Okay, so it's 11:02 and I will now really start with my lecture. My lecture about route planning algorithms, the basic techniques. This is a kind of introduction into research of the last 20 years about route planning algorithms and in particular the basic algorithmic techniques, so-called speed-up techniques for Dijkstra's algorithms. You will hear more about this in a minute. Matthias already mentioned in the last talk the importance of these kind of techniques. And so let's look at our scenario, our typical scenario, or the motivation for the techniques I will explain later. We know these navigation systems for cars. We know browser-based maps applications like Google Maps, routing maps, routing apps, but also timetable information. And from the perspective of public transportation, of course, the timetable information systems such like the DB Navigator app or such machines at stations are more relevant or seem to be more relevant than navigation system for cars like this TomTom system. But at a certain point, these systems come together when we want to combine the different modes of transportation and want to have information about the best routes in a combined transportation network. So this is one reason why looking at navigation systems for cars or route planning algorithms in street networks makes also sense for public transportation, multimodal route planning on one hand, but the other reason why it makes sense to look at the simpler scenario of road networks is that those techniques that were developed for route planning in street networks or route networks are also relevant for timetable information. So let's look first at the model we consider. So the basis for this talk is typically a road network, like here, part of the city map of Karlsruhe. And we want to find the best connection between a source node and a target node in such a street network or road network. And what we do is, in order to come up with algorithms for this scenario, is we model this road network as a graph. The street intersections become vertices or nodes, and road segments become edges, typically directed edges, although in this example I leave out the directions. And then we have edge weights, which usually are the travel time, the time it takes to travel from this point to this point along this road segment. But the weights could be also something else, for example, the distance in kilometer or meter, or it could be also something completely different, like the power consumption of an electric vehicle that wants to go from here to here. But in our scenario for this talk, it's typically the travel time. And then the problem is to find the best connection between a source node and a target node, which is the same as finding the shortest path in this graph we just built up. So here we are looking for this best route between source node S and target node T. Okay, so how to find this best route? The first answer is the classical Dijkstra's algorithm. Find such a best route. In the introduction on Monday, Markus Friedrich asked the participants who knows Dijkstra's algorithm, and if I'm correct, roughly half of the participants said, yes, we know this algorithm. It's a classical algorithm. It's from 1959. And in computer science or informatics, we teach this algorithm already in the first year of the bachelor program. For what follows, you need not know this algorithm in all detail, but it helps if you have an intuition how this algorithm works. And therefore, I will give you this intuition. The algorithm explores all nodes starting from the source node in increasing distance. So the source node or origin, the connected nodes are explored in increasing order, increasing with respect to the distance of the origin. So at every step, another set of nodes is explored, and the red nodes you see, these are, well, the currently explored nodes that can be also called the search front of this search or this exploration. Okay, if we continue that way, at a certain point, we also will reach the destination node. You already see here what happens. A large part of the road network is inspected or explored by this algorithm before we reach our target node. Maybe I should explain once again in a bit more detail how Dijkstra's algorithm works. And in order to do so, let's look at this small toy example. This small toy example consists of certain nodes and directed edges. And here at the directed edges, we have weights, travel times. The source node is this node here. And in these little squares that I have put at the nodes, we will maintain the so far discovered distance of that node to the source node. So the distance of the source node to itself is 0. That's why we have a 0 here in this little square. And now, starting from the source node, we inspect the nodes that are connected or reachable by a directed edge from this source node. These are these two vertices. So in the next step, we have found that vertex, and we have found that from here to, from the source node to that vertex, it takes 5, yeah, because the weight of this edge is 5. And in the same way, from the source node to this node, it takes us 1 unit. And that's why we have now put 5, respectively 1, into this small squares. Here in the right part, I have a short description of the algorithm. The algorithm maintains the discovered nodes in a so-called priority queue. That's a data structure. And the ordering these nodes are maintained in the priority queue is by distance. So in this case, we would have put first this vertex in the priority queue and then this vertex. And then when settling the node, like we did here with the source node, we relax the outgoing edges and we try to improve neighbor distance. What does that mean? Okay, let's continue. Then maybe we understand what that means. So in the next step, starting from that node, we inspect the neighbors of that node, vertices that are reachable. So let's say first inspected that node, and we found out together with the distance of this first node, distance 1 to the source node, we have a distance 4 going here at that edge, distance 4 to this node. And the same way, distance 9 to this node. From the source node to this node, we found a way of distance 9. And here we improved the distance. Before, we only knew we can come from the source node to this node going via this edge of length 5. But now we found out we have a shorter path going via this node, and this has only length 3, distance 3. So we updated the label here to 3. So this is meant when we say improve neighbor distances. And if we continue like that, we next find this node at distance 5 to the source node, and then we relate this node, and so on, and we can end if we have inspected all the nodes. Well, in my toy example, I only talked about a source node and not about a target node. But what we usually want to find is the shortest path from a source node to a target node. Dijkstra's algorithm just does more than that. In this case, we just found the shortest path from the source node to all other nodes. So what we have in yellow here, these are the shortest paths from this node to all the other nodes, which is actually as a structure, a tree. Yeah, it's the shortest path tree from the source node S. Okay, if we do this in our instance, in our graph, we at a certain point find this shortest path from S to T by exploring all these other nodes. Exploring a large part of the whole graph. We can stop this exploration when we have reached the target node. But we see the problem behind this. Although computing shortest path in a graph is an easy problem from complexity state of view, from a graph theoretic or algorithmic point of view, that is an easy problem. It can be solved in polynomial time. Actually, Dijkstra's algorithms with the right data structures like a priority queue can do this very efficiently. But still, in a huge transportation network, it's problematic that this algorithm explores a large portion of the graph before it finds the shortest path. And this is just too slow for the scenarios we usually consider in transportation. We could do a little bit faster by applying some very classical improvement of Dijkstra's algorithm, that is not only start the search from the source node, but at the same time from the target node. So that way. And then when the two search spaces meet, we can combine the shortest path by the shortest path from the source node to this meeting point and the target node to this meeting point. So Dijkstra's algorithm can be directly improved a little bit with respect to running time. And what we did here is an important building block also for route planning algorithms that are much more sophisticated, but it's not enough to for these scenarios or applications we are interested in. So let's look again at what are we interested in. Well, the typical applications perform many queries against the same unchanging network or graph. Yeah? So the scenarios we look at is a street network or timetable, and many queries need to be answered within very short time, queries for best connections, while the underlying road network or timetable doesn't change. We will see later that this is not completely true, but for the next, say, 30, 40 minutes, let's keep the assumption that the graph doesn't change. And now we want to apply basically Dijkstra's algorithm, but it should be much faster than the pure algorithm or the redirected version. Needs to be much faster. And the idea is the following. We first introduce an offline preprocessing phase. And in this phase, we pre-compute additional information that can be used to speed up the queries, that can be used, say, by Dijkstra's algorithm to find the shortest path faster. In such a scenario, there are three criteria of importance. This pre-processing time, the time it requires to pre-compute the additional information, the space required to store this information, and then, of course, the speed up of a Dijkstra's algorithm we can reach that way. One easy, very, very easy way to apply this this strategy would be to pre-compute in the pre-processing phase all shortest paths, all shortest paths between pairs of nodes. In this case, the query would be very fast in constant time. You just would have to look up, if we want to find the shortest path from S to T, we have to look up in our pre-computed data structure, so just the result. But this is not practical because the pre-processing time for computing all pairs shortest path is too large to be practicable, but even storing all shortest paths requires in the scenarios we are interested in too much space. So this is not really an option, but it's a nice consideration, just nice exercise to think of this idea, to think about this idea. I will give you in my talk a few ideas how one can come up with such techniques, such speed-up techniques for Dijkstra's algorithm. And these ideas are engineered over the years. So it's maybe worth to talk for a few seconds about the methodology behind this research. The methodology is algorithm engineering. And this combines both algorithm theory, so finding a nice model for the problem you want to solve, design an algorithm, analyze the algorithm from a theoretical point of view, with, well, the more practical or application-oriented part of this approach, implement the algorithms, perform experiments to find out how fast they really are. And if you're happy, or if you're lucky, you find out by the results of the experiments how you can improve your algorithm. So go through this cycle again and maybe once more to come up with really practical methods. In the following, I will give you results about how fast the methods are we have developed. These results are based on experiments, experimental evaluations on basis of real-world data. So this is this practical part. On the other side, I won't talk much about theory, but please keep in mind there is some theory behind. We are talking about algorithms speeding up Dijkstra's algorithms, so the results are new algorithms or new algorithmic methods. And one very important aspect is that these algorithms still should guarantee that the path they compute is indeed the shortest path or the best connection. So the correctness of Dijkstra's algorithm should be maintained. Yeah. So I won't talk about this part of research, but behind the methods I will present, there are correctness proofs, yeah, that are required in order to really guarantee that the results are really best possible. Okay. Now, Matthias mentioned an overview article from 2016 by Bast et al. And in this article, there are lots of speed up techniques that are applicable for route planning in road networks. There are also techniques tailored for timetable information. And this table is shown in this survey article. From these techniques mentioned here, arcflex, multi-level Dijkstra, ALT, contraction hierarchies, and so on, I will explain in more detail multi-level Dijkstra on one hand, and contraction hierarchies on the other hand. I will also shortly mention hub labeling. Timetable information techniques like transfer patterns, Raptor, connection scan, and so on will be explained in more detail in the subsequent talks by Jonas Sauer this afternoon. Let's take a short look at this table. Here are these many techniques listed here, somewhere placed in this table, where on one hand we have query times, on the other hand we have preprocessing time. I talked about the criteria that are of importance here. It's preprocessing time, it's query time or speed up over Dijkstra's algorithm. And the third criteria, space consumption, is not shown here. And here you see, for example, there is this technique hub labeling, which seems to be very, very fast, but requires quite some preprocessing time. Other techniques like CCH, CRP are slower, but don't need so much preprocessing time. So it's something about a compromise between these three criteria. And this table is in particular of interest for those who take the whole problem as kind of competition. Which technique is the fastest techniques? But we in our talk, we take this problem more from the perspective of people or researchers who really want to come up with techniques that are of relevance in practice. And actually the techniques I will concentrate on, multi-level Dijkstra and contraction hierarchies, are of relevance in practice. Nowadays they are in use in map services like the Apple Maps, Microsoft Bing, Google Maps, but also devices by TomTom and so on. Okay, before we go into multi-level Dijkstra and contraction hierarchies, only one word about another classical speed-up technique. That's the technique A* or goal-directed search, a technique also from '68, so it's a quite old technique. This is the first speed-up techniques for Dijkstra's algorithm, one could say, and the idea behind this technique is the following. As I told you, Dijkstra's algorithm uses as basic data structure a queue where the inspected vertices are ordered by distance to the source node. And the idea of goal-directed search, or A*, is to add an appropriate potential to this distance. So not ordered by just by distance to the source node, but by the value of this sum, distance to the source node plus the potential of the vertex. The potential depends on the target node. And then if we have this potential function, wherever it comes from, the vertices or nodes are traversed considering instead of the distance, this value distance to the source node plus the value of the potential. The performance with respect of what's the speed up of this technique depends, of course, on the choice of this potential. A few words about this potential, therefore. Perfect speed up is perfect if this would be just the distance to the target node. But this is something we don't know. We don't know the distance to the target node before we compute the shortest path from the source node to the target node. But if we would know it, then this would give us the perfect speed up, because within one step we would know the distance from S to T. Yeah. Dijkstra's algorithm doesn't use this potential. So one could interpret what Dijkstra's algorithm does as it uses the potential 0, the function that gives all the nodes the value 0. Now, something in between this distance to the target node, which we don't know, and the potential 0 is what we maybe can apply, and that which could have an effect on the performance of Dijkstra's algorithms. So we need some sufficiently tight lower bounds for the distance from each vertex to the target node. Correctness, I mentioned before that everything we do should keep the correct shortest path. Should guarantee that what we compute is really the shortest path. This potential H is something like a heuristic function, but it's heuristic in the sense that if it's chosen appropriately, it results in a speed up of Dijkstra's algorithm, but we don't know how large the speed up is. If we use some arbitrary potential, it may lead to wrong results. In order to come up with a guarantee for correctness, let's have a short look at this consideration. If we apply A star on our original graph with the original length function on the edges and an additional potential HT, which here, for example, is the potential of S is 1, potential of this node is 2, of this node is 1, of this node is 2, and this on target node is 0, then the result is the same as if we would apply Dijkstra's algorithm on the same graph, but with slightly modified edge length. Here the new length function is the original length minus the potential of node U2 with respect to T plus the potential of node V with respect to T. So applying A star here with these potentials is the same as applying Dijkstra's algorithm here with this new length function. And from this consideration, we can deduce that a heuristic function HT is feasible, say guarantees shortest path, if the length function minus length from of the edge UV or distance UV minus the potential of U plus the potential of V is non-negative for all edges. At that point, you might say, well, No, okay. No, let's continue. So non-negative, that's what we need here. Okay. So what the speed up we can achieve with goal-directed search, or A star, the other name of this technique. Well, this ends up with query times of 10 to 100 milliseconds, which is something like 2 orders of magnitude faster than Dijkstra's algorithm. That's not bad. Yeah, that's not bad, but it's still not enough. There are heuristics based, or there are methods based on A star, like the method ALT. Potentials that can be used are, for example, the Euclidean distance between the nodes. That's easy to get. But the technique, contraction hierarchies, we will see later, can also be used to come up with nice potentials for goal-directed search or A star. I mentioned hub labels before as a technique that is very fast, but not practical. So only one word about hub labels. It's different from the techniques we will consider in more detail, because it's not directly a speed up techniques for Dijkstra's algorithm. The way the shortest path is computed based on hub labels is different than applying Dijkstra's algorithm using some additional information. The idea behind hub labels is the following. We select a certain set of hubs and store for each vertex the distances to these hubs. So from S, we store the distances, or recompute the distances to these blue nodes that are somehow selected, and from T, the distances to these green nodes. And the only thing we have to take care of is that the distance labels, or hubs, are chosen in such a way that the cover property is fulfilled for all vertices. And that means if we select the source node T and the target source node S and the target node T, the following property needs to be fulfilled. The intersection between the set of labels for S and the set of labels for T is not empty, and in particular among the nodes in this intersection is at least one node that lies on the shortest path from S to T. Well, why is this useful? Well, it's useful. Let's look at this example. So here is one node in the intersection of the labels for S and the labels for T. And if this is really a node that lies on the shortest path from S to T, you can easily, using this node, compute the shortest path from S to T. Just take the shortest path from S to this node and the shortest path from T to this node, and then combine these shortest subpaths, and that way we get the shortest path from S to T. Which means, in other words, is we have these labels for all nodes. A query can be answered just by one coordinated linear sweep through this intersection, this set of nodes that lie in the intersection of the two set of labels. Now, how to come up with these labels or hub nodes, that's another question, a question I will answer later. If we have a good set of labels, then the query can be very, very fast. It's only 5 times slower than just looking up the shortest path in a pre-computed set of all shortest paths, which means it's a speed up over Dijkstra of 6 to 7 orders of magnitude. That's a factor of 1 million to 10 million. This is really fast, but the drawback is the space consumption is impracticable. The same holds for the pre-processing time. Both are not practical. But this is more or less the fastest one can reach. Okay, now, as I told you before, we will go into two methods or techniques. One is multi-level Dijkstra, the other is contraction hierarchies. Let's start with multi-level Dijkstra, or with other words, using so-called overlay graphs. Well, for finding shortest paths, it seems that some nodes are more important than others. Some nodes lie on many shortest paths, while others are not important in the sense that nearly no shortest path goes through these nodes. So these more important nodes, let's concentrate on these more important nodes. So I said importance, that could mean a node lies on many shortest paths. If we look at a road network or transportation network, bridges, for example, are very important. If I want to travel from Karlsruhe to Trier, where my mother lives, I have to pass the River Rhine at a certain point. So I have to use one of the bridges over the River Rhine, and there are not so many bridges over the River Rhine. So from geographical point of view, nodes are important, or roads are important, where many shortest paths go through because of the geographical situation. And in an abstract graph where we want to compute shortest paths, well, nodes that lie on many shortest paths are of importance, but where they come from, that's something we maybe have an intuition for, but we can't say much more about this at that point. But if we have this intuition, some nodes are more important than others, we could follow the following approach: build up an overlay graph by using an appropriate subset of nodes, the important nodes. Here, for example, the green nodes, and then pre-compute the shortest path between all pairs of green nodes and store these shortest paths or distances, which means in the overlay graph, we just introduce the direct edges or shortcuts between the green nodes. And then for a query, we just apply Dijkstra's algorithm, bidirectional Dijkstra's algorithm, but only stay as soon as possible in this overlay graph. So starting from S and from T, we start with Dijkstra's algorithm, but as soon as we reach one of these important nodes, we are in the overlay graph and we stay in this overlay graph, which means we only expect these direct shortcut edges, which is less than inspecting all the nodes and edges in the original graph. Here, the search would look like this, which means the search space is compared to the search space of the original algorithm of Dijkstra much sparser, much smaller, much sparser. Of course, when we have found in the overlay graph the shortest path, we have then go back to the original graph and unpack the original shortest path. The question is this already fast enough, or can we be faster using these overlay graphs? Yes, we can, by using a hierarchy of overlays. And this is multi-level Dijkstra. So let's go back. We have this important green node, and among these green nodes and this overlay graph induced by the green nodes, we choose a smaller set of the more important nodes among the green nodes, these blue nodes, and then compute an overlay graph induced by these blue nodes by, again, recomputing the shortest path between pairs of blue nodes and introducing the induced shortcut edges, and then maybe another level, choose these red nodes, which are the even more important nodes within the blue nodes and compute the induced overlay graph for this red nodes, well, and so on. And then we have, well, more something like a flexible framework for route planning. So based on multi-level choice of important nodes, we can apply Dijkstra's algorithm. And one more word about the important nodes here. In the multi-level Dijkstra approach presented in this paper by Frank Schulz, Christoph Zarouliakis, and myself, we used separator nodes or separator decompositions. I just mentioned important nodes in the road network are, for example, the endpoint of bridges, because we often have to pass bridges. If we would delete the bridges from a road network, we would decompose the road network, into the part to the right of the river and to the left of the river. And this is the intuition behind this multi-level separator decomposition. Just partition the set of nodes such that we get cells, and the border nodes are these overlay nodes or important node, and shortcuts between these nodes. These are the shortcuts we need to build up the overlay graph, and we do this recursively. So here we have the intuition important nodes. These are something like separated nodes, or nodes that separate the network. The query times one can reach using multi-level Dijkstras are between 1 millisecond and 10 milliseconds. This is a speed up over Dijkstra's algorithms of 3 orders of magnitudes. And here we start to be practical, say, with respect to this compromise between processing time, space required for the additional information, and speed up. Although I don't talk about the preprocessing time and the additional space required here, the experiments show that this, what we have here, what we can reach here, is practical. Now let's talk about the other approach that's relevant today besides multi-level Dijkstra. The other approach is contraction hierarchies. And this is also an approach that works with overlay graphs, but the overlays are computed quite differently, although we will see later that these two techniques, multi-level Dijkstra and contraction hierarchies, have a lot in common at the end when they are engineered to perfection, say. But let's go back to this work of Geisberger, Delling, Schultes, and Sanders, where contraction hierarchies are presented for the first time. The idea is to heuristically order the nodes in the network by importance, again, by importance, whatever that means. And then construct a contraction hierarchy by, well, constructing one overlay level per node. So in this example, these nodes are somehow ordered by importance, and then these overlays are constructed by contraction. So let's look at a toy example in order to understand what contracting a node means. We iteratively contract nodes by ascending importance. And contracting a node is what we will do now with this node X. We look at the neighbors of X. And what we do when we contract X is we will remove X and all incident edges and introduce instead new edges that are induced by shortest path between neighbor nodes of X that go via X. For example, here, from this node via X to that node, we have a path of length 5. So we introduce this edge of length 5. Same here. Let me see. Here, from this node to this node, we have a path of length 6 that goes via X. Therefore, we introduce this edge of length X. Same here, an edge of length 8, and these additional edges of length 6, respectively 5, and so on. In the next step, we observe that some of the edges we have introduced are not really required. For example, here, no, one step back, that if we introduce these new edges, that other edges that are already in the network are not really required. Here, for example, we already had an edge of length 6. There is this edge of length 5 induced by shortest path via X. So this edge of length 6 that is in the original graph is no longer relevant. While here in this case, we have introduced an edge of length 8. We already have an edge of length 7. So this new edge of length 8 is not really relevant. Okay, so what we end up after contracting X is this little graph. Okay, we could go one step further. For example, here we have introduced this edge of length 6, which was induced by a shortest path from that node to that node via the contracted node X. But it could be that somewhere in the network there is some other graph, there is some other path from that node to this node, which is even shorter. Here we have a path of length 5. So this edge of length 6 is not really required for computing shortest path. So one could even say, well, before I have a very dense network with many, many additional edges, let's also inspect the graph if somewhere else there are shorter paths than the edges I have introduced. That's something we can do but need not do. It doesn't harm to keep this edge in the network. It wouldn't spoil correctness, but it spoils efficiencies. That's why in this original paper, this additional search for shortest paths in order to sparse the graph applied. Okay, if we apply contraction hierarchies in our street network of Karlsruhe, we come up with this overlay graph. And then, of course, the question remains how to find the shortest path between source and target node. And the answer is easy, just apply bidirectional Dijkstra in this contraction hierarchy, in this overlay graph. Only traverse edges to more important nodes within this search, which means we get a more efficient search space than in the original graph if we use this contracted graph. So here, this bidirectional Dijkstra in the overlay induced by contraction hierarchy would look like this. So the search space is much smaller than the original Dijkstra search. Okay. Yeah, here again, we used importance, the notion of importance. So what is a good importance ordering of the nodes? A small search space, but not too many shortcuts. This is what we want to have for our, at the end. And in the paper of Geisberger et al., the approach was kind of bottom-up order first take unimportant nodes, then more important nodes, and so on, and then greedily construct the nodes which insert the fewest shortcuts. And nodes are important, for example, when they lie on one shortest path. So one could somehow try to compute in a pre-processing nodes that are more important than others. So compute many uncovered shortest paths and assign highest importance to node covering most of those. This is somehow the approach that was used in the original contraction hierarchy papers. The experimental evaluation leads to an extreme search space reduction. We have here query times that are below 1 millisecond, which means we have a speed up over Dijkstra of 4 more orders of magnitude. This is really practical. One could also use this approach to come up with nice distance labels for the hub labeled approach. Because it turned out that upward search space, the upward search space from contraction hierarchies induces very nice labels. They are not minimal, but can be pruned during the preprocessing. So this is just a side remark in order to show you that these different techniques are somehow combined or intertwined with each other. I should mention here that this talk in a way also covers or is a review of, say, 20 years of research I also did myself together with PhD students and co-workers. And again, we had these moments where we found out that some insights we had 5 years ago could be nicely combined with new insights. And so somehow we came up with these techniques that are even of practical relevance today. Okay, so far, what I explained was more or less about computing shortest path in a graph. Although we have this example of a street network of Karlsruhe, I didn't talk much about traffic or transport scenarios. If we really look at traffic scenarios, we see the following problem. I made the assumption that our graph doesn't change. Yeah? But this is, of course, not true. Traffic changes all the time. So if the relevant metric we consider is travel time, so the edge weights or length at the edges are induced by travel time, then the assumption that the graph doesn't change is no longer true, because the travel time changes over the day, the week, can change because of some accident, whatever. But the pre-processing phase we applied in both techniques, multi-level Dijkstra as well as contraction hierarchies, and also all the other techniques, heavily depend on these edge weights, yeah, on the metric. And of course, the pre-processing time is too slow to, well, apply this pre-processing again and again whenever the traffic changes. Yeah. Pre-processing is too slow for frequent updates. So we need some other idea. And the idea or the solution is the following. Let's concentrate on the pre-processing and let's analyze which part of the pre-processing really depends on the metric. And if there are, on the other hand, parts of the pre-processing that do not depend on the metric. And let's split or separate these two parts into two separate phases. So So far we had this two-phase approach, a preprocessing and then the fast query, two phases, preprocessing phase, query phase. Now we have a three-phase approach, the metric independent preprocessing as a first phase, then the, well, what's called customization as a second preprocessing phase that needs to be much faster. That is just depending on the weights or edge lengths. It should be only a few seconds or less. And then the third phase, the query phase. Okay, so how to split the preprocessing into two phases. In contraction hierarchies, the preprocessing very much depends on this contraction order or node order, this notion of important nodes. This node order and how it looks like and how we come up with this node order is really critical for the performance. And it usually depends on the metric. The node order usually depends on the metric. The question is, can we come up with a node order that is independent for the metric, or in other words, which is good for every metric? Sometimes theory helps. There's this notion of nested dissection, also in theory, a very old notion. And it's actually depending on separating a network, something we already talked about before, separating the network or using separator node. Let's look at this toy example. Nested dissection on this toy example is the following. We want to separate the graph into two parts of equal size by deleting a small set of nodes. Here, if we delete these three nodes, we just can separate the remaining graph in two parts of equal size. If we do this recursively, say first on that side and then on this side, or the other way around, first here and then here, can come up with a separator of size 3 here, and so on and so on. So it's a recursive procedure, recursively bisect the graph. And important is the observation that separator nodes are in a way important. I already told you that bridges in a network, in a street network, are on one hand important for the traffic, on the other hand, are separators in the way, because if I delete all bridges, this separates the network. And this is the idea here behind using nested dissections. The separator nodes we delete first are most important in the complete graph. So in our ordering by importance for contraction hierarchy, they are the most important ones. So they are put at the end of our ordering, because contraction hierarchies at the beginning contract the least important node, and then by ascending importance, the nodes are contracted. So the important node, the separator nodes are at the end of the ordering. And then just consider the two parts, the two remaining parts completely separate. So separate. And so continue separating this part and then this part. If we have good separators, these are separators that on one hand separate the graph into almost equal parts of equal size and are small on the other hand, then we can even come up with theoretical results about the search space, the size of the search space, or the speed up we can obtain. So if we have small separators of size n to beta, say, for example, n to 1/2 square root of n, then we can guarantee a search space reduction of the same size or order. In road networks or in practice, small balanced separators come from the geography, rivers, mountains, highways, and so on. So the whole part of research just concentrating on finding good separators for road networks, good in the sense that they result in nice contraction hierarchies or nice multi-level Dijkstra frameworks. So back to contraction hierarchies. We want to apply this three-phase approach where the preprocessing phase is separated into two phases, the metric independent phase and the metric dependent phase. The metric dependent phase is customization. Yeah, the metric changes, so we have to customize our contraction hierarchies. And the answer is how to do this. Use nested dissection. So recursively bisect the graph and then assign highest importance to the separator nodes. Yeah. So in this map or road map of Karlsruhe, the first separator would be these black nodes, which separate Karlsruhe into the brown and the blue nodes. And then again, separate these two parts and again and again. Okay. Now, what does it mean in detail? So let's look at a toy example. We want to apply the preprocessing where we compute the nested dissection order and then create all possible shortcuts. Again, theory helps. What we do here is a well-known technique in graph theory, the so-called graph fill-in, which, by the way, if we look at graphs or look at the matrices, adjacency matrices of the graphs instead of the graph themselves, what we do here when we apply graph fill-in is the same as what is done in Gaussian elimination when we want to solve linear equations. So back to the graph here, we have a small toy example with nodes 1, 2, 3, 4, 5, 6, 7, and this is also the order we apply. So we first contract 1, and because now we look at the graph without edge lengths, yeah, we just add all the induced edges, the edges induced between neighbors from 1 from the path that would go via 1. Yeah? And next we contract 2. So what we get as additional edge is this edge between 5 and 7. And so on. If we contract 3, nothing happens. If we contract 4, we get an additional edge from 1 to 5. From 6 to 5. We only consider in the later stages those nodes that are not yet contracted. So I have kept 1 and 2 and 3, although they are already contracted before we consider 4. So we have to ignore them when we further contract. Okay. And now this is what we get if we apply contraction, like in contraction hierarchies, but just without considering any edge weights. That just means we introduce these fill-in edges, nothing else. In the second part of the preprocessing, the weights come in, or the metric come in. So how to introduce the metric for such additional edges? We have to compute the shortcut weights for these shortcut edges. In order to do this efficiently, we just have to iterate over all edges by ascending importance, which in other words means we enumerate and relax the lower triangle of each of these edges. In order to do this, let's draw this graph differently. The least important nodes, those that are contracted first, are at the bottom, and then with increasing importance, they are placed higher up in this drawing. And in order to introduce the metric, we consider the nodes from bottom to top and just look at the lower triangle of each of these nodes. So we first introduce the metric, our original metric, like in this graph, we have certain edge weights, and we are interested in the induced length of the new edges filled in. Yeah. At the beginning, initialization just assigns infinity to these edges. And now we inspect the vertices from bottom to top and look at the lower triangle. When we inspect one, well, there is no lower triangle because one is on the bottom of this graph. Same holds for 2 and 3. But when we inspect 4, we find this triangle, this lower triangle from 4 via this lower vertex 1 to 6. And the according path introduces the weight for this additional new edge. So we place weight 2, this dashed edge from 4 to 6. The next step, we inspect this lower triangle via from 4 via 1 and get from this triangle edge weight 11 for this new edge from 4 to 7. And so on. So next we inspect 5. The lower triangle, one lower triangle we find is this one, and this induces weight 3 to this edge between 5 and 6. Another triangle, lower triangle, that induces a new weight for this edge between 5 and 7. 12, 1 plus 11, and so on. That's something that can be done very, very efficiently. So customization is nothing more than iterating over all edges by ascending importance and just enumerate and relax the lower triangles. Over all vertices should be by ascending importance and just enumerate and relax the lower triangles of these vertices. Just as a side remark, when we looked at nested dissection or this separator decomposition, I said after the first separation, we can look at the two parts to the left and to the right of this small separator we had independently. And this means this can be parallelized. Yeah? So to be faster in this part of the preprocessing, we can just use parallel, like maybe several cores in parallel. Okay, when we apply this customizable contraction hierarchies in our Karlsruhe graph, it looks like this. It's a little bit disturbing. How does the query look like? We had in contraction hierarchies, we had Dijkstra-based query, just a bidirectional Dijkstra that can be applied also in the customizable contraction hierarchy approach. But we can be, well, more clever. Yeah? one step back. So this Dijkstra-based contraction hierarchy query is applicable without modifications, but it's a bit slower than in the original contraction hierarchy. And the simple reason is that because of this fill-in procedure to fill in the additional edges while contracting vertices, we have more edges in our overlay graph than it was the case in the original contraction hierarchy, where a lot of additional computation was done in order to keep the graph, the overlay graph, sparse. But the whole approach also induces a completely different or alternative query algorithm. And this is really nice. We can use something that is called a data structure that's called elimination tree. And this is also comes from this old theory about graph fill-in, the graph fill-in approach we used here. A data structure that's induced by the graph fill-in. Just look at our graph and the order we looked at the vertices from bottom to top. If we just take these vertices and only those edges that are edges from a vertex to the lowest ranked upward neighbor, then we get a tree. Yeah? A tree. So the ancestor in this tree is the elimination tree, and the ancestors in this elimination tree just induce the search space of contraction hierarchies. So on the right side, we have this induced elimination tree just from each vertex, only the edge to the neighbor of lowest rank. So from 1 to 4, from 2 to 5, from 4 to 5, and so on. And then we can just use this tree in order to compute the shortest path between S and T. And this is just done by traversing this elimination tree from S and from T to the root. So if 1 would be S and 2 would be T, we would just traverse from 1 upward and from 2 upward until we come to the root. So we don't need this data structure priority queue that is used by Dijkstra's algorithm. So no additional data structure, we just can use this elimination tree. And one advantage of this is that it can also be used if we have negative weights. Dijkstra's algorithm doesn't work with negative weights, but using this elimination tree approach, we can even consider negative weights. Now is the moment that you may ask, well, negative weights in a transportation networks, that would mean negative travel time. Only in science fiction we can travel backward in time, so negative travel time doesn't make sense. Negative distance, that also doesn't make sense. Well, there are scenarios where negative weights come in, and this is in route planning for electric vehicles. If we look at the power consumption of electric vehicle and take this as our relevant metric, then we really have negative weights. But this is only a side remark. If we use this elimination tree approach in our example, it looks like here, it's a little bit disturbing, this elimination tree that are the solid black edges. We traverse this elimination tree from source node and from target node upward until we come to the root of this tree, and we elect the outgoing edges for each of the nodes we consider. So what we have, the result we have is this 3-phase speedup technique that can be used in real traffic scenarios where the travel times change over the day. a metric update costs around 1 second. So this is this customization phase. It costs around 1 second. This is fast enough. And it works very well for different metrics, not only for travel time. This is also nice. And the elimination tree query is even slightly faster than the contraction hierarchy query, which is based on Dijkstra's algorithm. So this is nice. And this brings me to the conclusion or the end of the talk. I tried to give you some insights into the research area of fast route planning algorithms. I concentrated on road networks. We looked at A*, at hub labels, and in more detail at multi-level Dijkstra and at contraction hierarchies. We also considered the conditions that come in when we look at real traffic scenarios, that is, that the metric can change. And I explained how contraction hierarchies can be further engineered to be applicable in this scenario. And the result was customizable contraction hierarchies. Multi-level Dijkstra can be also applied as in such a scenario. So there is also this customizable version of multi-level Dijkstra. Actually, historically, it was even the first customizable technique. And the fastest techniques we have for computing shortest path or route planning are up to 6 orders of magnitude faster than Dijkstra's algorithm. But those techniques that are 6 orders of magnitude faster than Dijkstra are not practical for other reasons, because of the speed of consumption, because of preprocessing time. But the practical methods like multi-level Dijkstra and customizable contraction hierarchies, they yield speed ups of 3 to 4 orders of magnitude in comparison to Dijkstra's algorithm, with space consumption and preprocessing times that are practical. So what comes next? There are many new challenges, and from the perspective of public transportation, we have to, again, to look in more detail about the basic scenario timetable information. And Jonas will do this afternoon. Of course, one could say, well, let's model a timetable as a graph and then apply these techniques. This is possible, but it turned out over the years that there are faster techniques that are tailor-made for timetable information. But as soon as we want to combine different modes of transport, as soon as we consider multimodal route planning, of course, road networks come in again, and these techniques like multi-level Dijkstra and contraction hierarchies have to be considered again, now in combination with tailor-made timetable information methods. But there's a lot more to be considered, like incorporating alternative mobility concepts. Matthias talked about this shortly, eco-friendliness, autonomous driving, and so on and so on. And this is all I wanted to tell you. At the end of my slides, there's not only this thank you slide, but also a lot of references. But let's go back to this conclusion and outlook. And now it's time for questions or remarks, if you like.